Let's wrap up section 2B with this last information. So we have this example 6 that says two friends take a 3,000-mile cross-country trip together, but they drive their own cars. Car A has a 12-gallon gas tank and averages 40 miles a gallon, while car B has a 20-gallon gas tank and averages 30 miles per gallon. Assume that both drivers pay an average of $3.25 per gallon of gas. The first question we want to answer is, what is the cost of one full tank of gas for car A and B? So the information that I need from the above statement is the amount that car A, the amount of gallons its tank will hold, and car A will hold 12 gallons, car B will hold 20 gallons, and it says that we're averaging a price of $3.25 per gallon. So the question is, how much will it cost to fill each tank? So car A, I've got 12-gallon tank, and I'm going to multiply that by $3.25 per gallon. So I have $3.25 divided by my unit of gallons, and I will see that my units will cancel out, and I'm left with my value just in terms of dollars, and that's what I wanted. What would it cost? So we just need to multiply 12 times $3.25. Same thing for part B. I've got a 20-gallon tank, and I know that I'm paying $3.25 a gallon, so I'll multiply that by $3.25 per gallon. And I know the way I have this set up that my units will cross-cancel, so the result is going to be in dollars, which is, again, my desired result, and all I need to do is multiply 20 times 3.25. So we figure out that car A, it costs $39 to fill its 12-gallon tank. For car B, it costs $65 to fill its 20-gallon tank. So let's see what else we want to find out about this. So the question is, how many tanks of gas would car A and B use, respectively, for the 3,000-mile trip? So think about setting that one up. So the question is, how many tanks of gas do cars A and B use for the trip? Well, I'd need to find out how many gallons they're going to use for this 3,000-mile trip. And once I find out how many gallons they'll use for the trip, then I can figure out how many tanks of gasoline they'll use for the trip. So to determine how many gallons it will take for the trip, you take the number of miles, the 3,000 miles, the number of miles for the trip, and divide that by the number of miles that they get per gallon. That will equal the number of gallons needed for the trip. Then, once we have the number of gallons needed, I can divide that by the tank capacity to determine the number of tanks needed for each car. So I've done the math down here. I've appended a page. So for car A to travel 3,000 miles and they get 40 miles per gallon, they would need 3,000 divided by 40, which is 75 gallons of gasoline. If I take the 75 gallons that they're going to use for the trip and divide it by the capacity of the tank, which is a 12-gallon tank, that would tell me they would need 6.25 tanks of gas. For car B, if they travel 3,000 miles and get 30 miles per gallon, if I divide those two out, car B would need 100 gallons to complete the 3,000-mile trip. And car B, since its tank capacity is 20 gallons, if I take the 100 gallons necessary for the trip and divide it by 20 gallons per tank, that means I would need 5 tanks of gas for car B. Last part of this problem, how much would each driver, car A and B, how much would they pay for the gas for the entire 3,000-mile trip? We found out that car A uses 75 gallons of gasoline for the entire trip, so if we multiply 75 gallons by $3.25 a gallon, we end up with a total of $243.75 total gasoline costs for car A. And if we multiply the 100 gallons that car B uses by the $3.25 per gallon. And notice the same thing is happening here with the units. The units are canceling out, gallons and gallons. I'm left with dollars, and 100 times 3.25 is $325. Work this next example, pause the video, and then turn the video back on to see if your answer is correct. But take a second to work this. Now remember, there's more than one way to work these problems. I just want you to be able to problem solve and come up with the correct answer. You may have used a totally different way of working this problem, but we've come up with the same answer. I started with the 70 beats per minute, and I wanted to change that to hours, maybe to a larger unit. Let's see if it would help with my calculations. So 70 beats per minute times 60 minutes in 1 hour allowed me to cancel out my minutes and get this into terms of how many beats per hour. So the 70 times the 60 gives me 4,200 beats per hour. So every hour your heart beats approximately 42 beats. Or 40, it's not 42, whoops, 4,200. 4,200 beats in an hour. So I took that and I kind of sat on that for a minute and I looked at, okay, if I live to be 80 years old, I wanted to change how many years I would live to how many hours that represents. So I started with 80 years times 365 days in a year, canceling out my years, times 24 hours in 1 day, canceling out my days, and that tells me if I live to be 80 years old, I will have lived 700,800 hours. That number's kind of hard to say, isn't it? So, in 80 years, my heart will, I will have lived 700,800 hours. So if that's the number of hours I will have lived, and my heart beats at 4,200 beats per hour, I can multiply those two values to come up with how many beats my heart would beat in 80 years. So see if you come up with this number, 2,943,360,000 beats. Remember, you have to have a unit. Now, what is this number? Is it millions, billions, trillions? Well, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces behind the 2, so that tells me I'm in the billions. So 2,943,360,000 beats in an 80-year lifespan. Quite a large number. All right, let's wrap it up with units of density and concentration. So when working with density, density describes the compactness or crowding. So if you were looking at a city, you might want to know how many people per square mile or people per square kilometer. That's the density of a population. Or maybe the number of bacteria per square inch or square centimeter in a petri dish. Or maybe if you have an animal, the number of fleas per square centimeter. I know that's kind of creepy, but these are all values or units of density. Now, concentration describes amount of one substance that's mixed with another. Like if you have allergies, you may watch the report on the news about, let's say, the mold count, and they might say it's 4 parts per million or 3 parts per million. And what that means is how many pollutants or how many molecules you have per 1 million molecules of air or of water or whatever the substance happens to be. So parts per million is something you'll hear, carbon dioxide in oxygen, something like that in the air. You'll also see it with medicine dosages, maybe 2 milligrams per kilogram of body weight, and you would see something like 2 milligrams per kilogram, and that would be used to help figure out a dosage for a particular person. Or maybe a liquid suspension, children's Tylenol or Advil or maybe Benadryl liquid. The suspension might say 10 milligrams per milliliter. So it would be 10 milligrams / per milliliter. Or even blood alcohol content. When that value is given, it's per 100 milliliters of blood. So 0.08 grams of, in this case, alcohol per 100 milliliters of blood. So density, compactness or crowding, and concentration is a substance mixed with another. So let's look at some examples. Remember that the word per means to divide. So if I want to find a population density, it's people per square mile, or people per square kilometer, or fleas per square centimeter. That per means I'm going to divide. So I'm going to divide the number of people or number of objects in that population by the area given. And that'll give me an object per square unit. So we want people per area or objects per area. So we just divide. In this case, Manhattan Island has a population of about 1.6 million people living in an area of about 57 square kilometers. So the first question is, what is the population density? The next question is, if there were no high-rise apartments, how much space would be available per person? And we want that in square meters. And then how much space is this in square feet? So question 1, what is the population density? Well, we're going to take the number of people, 1.6 million people, divide it by the 57 square kilometers and come up with the population density, people per square kilometer. So we end up with 28,070 people, 0.17. And since we're dealing with people, we need to just ignore that 0.17 there at the end and say that the population density is 28,070 people per square kilometer. Okay, so second question. What's the if there were no high-rise apartments, how much space would be available per person? So this is asking me how much space, which is the area, per division person. So I want to take that 28,070 people per square kilometer and invert that to find how many kilometers per person. So if I take the 28,070 people, which I got, which was people divided by square kilometer, and invert that to become square kilometers per people, remember this is a fraction over 1, then if I invert that fraction, I'll just flip it over, it becomes 1 kilometer squared over 28,070 people. Whoops, let me fix that. If we divide 1 by the 28,070 people, we come up with 3.562, and I get scientific notation that has an E with a -5 on it. We'll talk about what that means, but this number represents how many kilometers or how many square kilometers per person. So just inverting that fraction gives me how many kilometers per person, how many square kilometers per person. Now the 3.562 with an E behind it with a -5 means I have to take the decimal that's between the 3 and the 5, 3.5, and move it 5 places to the left of the 3. And if I move that 5 places to the left of the 3, I'll end up with 0.0003, and then the 562, and that's square kilometers per person. Now the question asks us to find that value in meters, and then how much is that in square feet. So the third part of this is to take that value of 0.00003562, which is square kilometers per person, and let's change that to meters. So I would multiply it by my unit equivalent of kilometers and meters, and that would be there's 1,000 meters in 1 kilometer, But that unit conversion does not give me square units. So do you remember that magic math that we did? We would take that fraction and square it to get it in square units. So I'll be able to cancel the units, the kilometers squared, and have my answer in square meters. So when I square that, the 1,000 squared is 1,000,000. Then I'll have meters squared at the top. And when I square the kilometer at the bottom, I'll have kilometers squared, which will allow me to cancel out my kilometers, my square kilometers. And that's my goal. So I'll have it in square meters. So I'll end up multiplying that 0.00003562 times 1,000 squared, which is 1,000,000. See what that comes up. So that gives us 35.62 square kilometers per person. Now let's take that, excuse me, not kilometers, we changed that to meters. Whoops. 3562 square meters per person. Now let's determine what that is in feet. Well, I looked up a conversion factor and I know that there's 3.28 feet in 1 meter. So I would like to cancel out my meters. So that's why I put the meter at the bottom. But since I need square units, I have to go back, do that really great math, and square that fraction. Square the 3.28 feet over 1 meter, square the top and the bottom, so I'll have my unit in square feet and my square meters would cancel. So the math that I'm going to need to do is the 35.62 times 3.28 squared, and that'll tell me how many square foot is available per person in Manhattan. Figure that value out. So the final answer being 383.27 square feet per person. So now think about that. That's not a lot of space. If you're in a room that's 20 feet by 20 feet, then that's 400 square foot. That's not a big room, and that is, as far as area goes, that's the amount of area that's available per person to live in if there were no high-rise buildings. For this last example, it's a mixture type problem dealing with the dosage of Benadryl. I would like you to work on this, write down your information, pause the video, and then turn it back on to see if your interpretation of this problem is correct. Okay, so this last problem says the antihistamine Benadryl is often prescribed for allergies. A typical dose for a 100-pound person is 25 milligrams every 6 hours. First question is, following this dosage, how many 12.5 milligram chewables would be taken in 1 week? You may have started this one differently, but what I chose to do first was to find out, well, how many hours were in 1 week? So I multiplied 7 times 24, because there's 24 hours in a day and 7 days in a week, to get 168 hours in 1 week. Once I knew how many hours I had in a week, I wanted to find out how many dosages would be in that week. And since you take it every 6 hours, I divided 168 by 6, and that told me I would need 28 dosages of Benadryl in a week. Well, a dosage is 25 milligrams. But the pills are in 12.5 milligram chewables. So every dose would involve taking 2 chewable tablets to get the 25 milligrams necessary for each dose. So there's 28 dosages and 2 pills per dose. So if I multiply those, I end up with 56 Benadryl pills would have to be taken in 1 week at this particular dosing. The next question was, Benadryl also comes in liquid form with a concentration of 12.5 milligrams and 5 milliliters. So following the prescribed dosage that was mentioned earlier, 25 milligrams every 6 hours, how much liquid Benadryl in milligrams would a 100-pound person need to take in a week? Well, earlier we found that we'd have to take 6 Benadryl pills in 1 week. Well, each of those pills is 12.5 milligrams. So 1 pill is equal to the 12.5 milligram per 5 milliliter concentration. So to figure that out, I just need to multiply the 56 pills times the 5 milliliters, which would give me basically the equivalent of 1 pill, to get 200 milliliters of liquid Benadryl in 1 week. So now I would like you to go to my math lab and work on the homework for section 2B.